Hello, overview here on the t-Inference procedures, again, using the study guide for this unit. A couple things here, when you look at the comparison between this and the z-proportion procedures, when it's the z-proportion procedures, you're again looking for samples that would be p-hats, which would be, could be percents for a sample, what percent of the sample um, agrees with the idea of having an open hour in your school day. That could be presented as a decimal, a part whole decimal. It could be presented as a fraction, okay, in terms of the sample itself. And those were part whole relationships in all cases, versus this unit, which is in the T procedures. What you're going to see is the samples will be X bars, and the X bar would be mean height, mean weight, mean distance, mean length, mean time, all those sorts of things where you will get an X bar and an S perhaps will be given to you. This is a sample standard deviation, which is really a defining characteristic of the T procedure. Again, what happens is the S standard deviation, the sample standard deviation, enables us to use a T, which is an estimation of the standard normal curve, versus if we had a sigma for the standard deviation, then we can use a Z. And a Z curve is that perfect normal curve in that it's the tallest, skinniest version of the normal curve we use, whereas the T, because we are estimating the spread with that sample standard deviation, we have to leave a little more room in the tails. So for instance, what we'd get is this might be the Z curve here, and the corresponding a T curve with, say, 10 degrees of freedom might look like this, where there's just a little more area in the tails and a little less area in the center, like that. And again, both symmetric, both have a bell shape to them, even though my drawing doesn't exactly look like it right there. But the T has a little more area in the tails. And so that's again a distinction on the curve itself, and degrees of freedom become an important piece in this unit because we use that T curve. So getting into an example here, common example that I'll use in class is just looking at what the average height would be in our school building. And so for instance here now for the one sample t-test, again, we'd have the 4 steps, and the 4 steps would be the 4 points of a typical FRQ, in terms of where each one would be. Each would have an EP and an I, and they would be the 4 points in a question. So typically a one sample t-test question will give you either some sample data, it'll give you an X bar and an S, or it'll give you a list of numbers. So for instance, it could give you a list of 20 individual heights in our building, and we would use that list of 20 to get an X bar and an S, most likely on our calculator. And then those X bar and S values would be used to test a hypothesis or to estimate a mu, which is the interval side of this. So let's just pretend, for instance, that we have an H naught, that the average height in our building is 68 inches. And somebody comes along and says, no, I think it's something else. They think it's 67 or 69 or whatever it may be, but they think it's something other than 68 inches. So now that we've established our hypotheses, again, similar to the proportion test, whenever we use a symbol, in this case, a mu here, we do have to tell the reader what mu stands for. So that in this case would be the mean height of all Minnetonka students. Again, this is not the population, it's not just Minnetonka students, but the mu is the mean height of all Minnetonka students. So again, it's the mean that's represented there. Step 2 here would be the type of condition. So the type here, this is a one sample t-test. And when it comes to the conditions, the SRS again is going to be something that would be stated somewhere in the question. Since we aren't collecting this data, they'd have to tell us that it was collected fairly and randomly. And so when you are verifying that condition for the reader, you just need to point out that it states in the question, and then just quote the question. Question states, quote, a random sample of 50 Minnetonka high school students. Okay, so it is your responsibility to show the exam reader, for instance on an AP exam, of how you know that to be the case, that it is a random sample. The second condition here, in terms of being fair to believe that the sampling distribution is normal, again, this relates back to the idea of sampling distributions. This would want to make sure if we don't have a normal population like ACTs, that we are creating a sampling distribution, again, which is thousands of samples that would have a mean that would ultimately be normally, means from all of them. If you graph the means, those means will be distributed normally. Now, the way that's verified in this unit is one of three ways. The first is they'll tell us, and they'll tell us by either saying that it's been a sampling distribution has been created and it appears to be normal, or they might say that they created a box plot or a histogram and the histogram doesn't show any big outliers. But there would be something where they just tell us. Okay, and again, this is for this condition here. So tell us would be the first way we know. The second is if n is 30 or more, then we can just note that if n equals 50, like I said in this case, so that's greater than or equal to 30. And so what that does is that affirms that we have a large enough sampling size to have that central limit theorem go into action and assure a normal sampling distribution. If we do not have either of those, then we have to go to the third option, which would be to graph something like a box plot. Okay, in the box plot, what you're really looking for in the box plot are that there are no outliers. And again, keep in mind that the closer the sample is to 30, the better off we're going to be in terms of quote unquote fixing the shape, in terms of making it normal. If the sample's 29, then this box plot could be pretty ugly and we would be in pretty good shape because the sample's still pretty big. If the sample is 5, then this box plot would need to be closer to being symmetric because we just don't have big enough samples to get that sampling distribution to be normal. Largely because if we have one outlier in this data, say that there's somebody who's 6'7" in here, if that 6'7" person is in a sample of 28 others, well, that waters that down pretty significantly. Versus if that 6'7" person is in with 4 others, well, then their sample height might still be 6'1" or 6'2", which would never happen in a sample of 30 from our building. So that's how we verify the normality. Just like with the proportion, but even a little less so here, there is technically this 10n is less than capital N, which just says that we took less than 10% of the population, so we can assume that they're all going to be independent of each other. We didn't pick such a large group of people that there might be siblings or other groups that are going to skew the data because those pair of siblings are really tall or really short or whatever it happens to be. So that would be the second, is to verify those conditions along with identifying the type of the test. The third point here is in the calculation. And again, the X bar and the S would either be given to you by saying that the mean and standard deviation of the sample was this. It might just list X bar and S, or it might give you a table that has mean and standard deviation, and the table has a sample element to it where you can see that it's a sample. Or you may be given a list of numbers and have to find those values. Okay. The mu is going to be that hypothesized value here. So that would be 68 in our question. And the n is going to be the size of the sample that you selected. So for this problem, we talked about using 50. So we might get a sample that is a height of 67 minus 68, and they may have a standard deviation of, let's say, 3 inches in that sample, divided by the square root of the sample size. Now, to get that value, it's probably easiest, similar to other inference procedures, to just go to your calculator and go to Stat, Tests, t-Test. And with the t-Test here, what you're going to do is it's going to ask you about data or stats. Data means that you are given a list of numbers and you put them into a list. Okay, so it's going to ask you for the list. Versus stats is going to ask you for an X bar and an S. Okay, so in that situation, you will put in the mean and the standard deviation along with the mu. So in this case, the 68 is the mu sub 0, and then the n would be 50 that we talked about. You'll put in the alternative hypothesis, which in this case was not equal, and then you calculate. So for our example here, I would put in 68 for the mean, the mu sub 0. I'd put in 67 for the X bar. I'd put in 3 for the S, and I'd put in 50 for the N, and it would be a not equal to, and I would calculate. So when you calculate this, it gives you a test statistic then of about negative 2.36, approximately negative 2.36, a p-value of approximately 0.0225, and the degrees of freedom part here You can see n minus 1, that's just sample size minus 1, so there would be 49 degrees of freedom here. Note your chart for this does not have 49, and so you wouldn't really want to use that chart for anything right here. You just note 49, and then you take the test statistic and p-value from your calculator. Again, p-value in this case is if we look at this as a normal curve, and we assume that the center is at 68, which would be a t of 0, and that's again from the hypothesis. We got 67, which was way down here, about 2.36 standard deviations below the mean. Now again, because it's two-sided, the p-value, half of it's here, so this would be 0.01125, I guess. And then in theory, because it's two-sided, there's this other side over here at 69 inches, which would be a positive 2.36, again, just 1 inch up below and 1 inch above, would be the same t away from in either direction. So that would also be 0.01225. And combine those give you your p-value of 0.0225. Again, p-value is the likelihood of getting a result that far out, assuming the 68 is true. So assuming the null is true at this point, that's what that p-value stems from. And in this case, because the p was low, we'll reject HO if we use a typical 0.05. So we'd say since 0.0225 is less than 0.05, we reject the null hypothesis. So there is evidence for HA. Again, the question here is always for HA. So you're always going to end with a statement that would say, so there's evidence that the average height at Minnetonka High School is something other than 68 inches. Now it looks from our sample that it may be shorter, but we don't make that judgment here. We just note that it's something other than 68 inches to speak to HA. Taking that same problem and moving it into an interval down here, we have a first step here that's optional, and it's one I like, but you don't. The AP exam would not grade it as long as you include the information you need later on in the problem. But for this, all I would say for the first step is just a thesis statement that I am going to use this sample to estimate the true mean height of all Minnetonka High School students. And again, what this is recognizing in the end is the idea that we're going to use 50 randomly selected students from Minnetonka High School to try to estimate the average height in our building. And so it's obviously a much easier, a quicker, cheaper way of trying to get this by just having to ask 50 students instead of 3,400. And we can come up with an interval that's pretty accurate. So our first point usually comes down in the typing condition, which would be the one sample t interval. The random sample, we'd still verify the same way as we did above. We'd have to quote the question if we get this, because we'll get either a test or an interval. We don't typically get both of them together. And then we'd have to verify that the sampling distribution is normal, which would be done through the same process as above. Either they tell us n is 30 or more, or we're going to get that box plot. Okay. Now in the calculation itself, again, degrees of freedom is still n minus 1, so that's still 49. And then we look at the formula. And similar to all other times, as long as you've identified that it's a one sample t interval, then you technically are not required to put in the values. And what's nice about that here is the x bar in this case was 67. The t star is actually not on your formula sheet because it doesn't have 49 degrees of freedom on your formula sheet. So if you used your formula sheet, you'd actually have to round down to 40. You can't go up to 50. It's got to be, you can't assume more degrees of freedom than you have. You have to round down. But as long as you use your calculator, that would be a t star anyways if you want it to be, and you don't have to put in a value. But if you've denoted that it's a one sample t interval, then it is okay to just go to your calculator to stat test t interval. And when you do that, then you would just you would use that the calculator to at a 95% confidence interval or whatever it happens to be to give yourself an interval. And in this case, that interval goes from 66.15 to about 0.85. Okay. And that would be all you need to write along with the degrees of freedom being 49. So this right here would be able to replace the formula as long as you have already identified that it's a one sample t interval in this case. Once you take that, now you can interpret it. And so in this case, since I use 95% confidence, I would say that we are 95% confident that our interval, and we just put that interval right in there, 66.15 to 67.85, contains the true mean height of a Minnetonka High School student. And again, that's talking about all 3,400 now. And so that will again be a generalization to your population, and a fairly accurate one, provided that we followed the conditions needed in order to make sure that our interval was valid. One thing we can do now, because this follows the two rules for comparing an interval to a test, the two rules being that the confidence level and significance level add up to 100%, and that our HA is not equal to. If we follow those two rules, then we can actually use the interval to answer a question about the test or vice versa. And how we do that here is when you look at our interval, note that our interval does not contain the number 68. Okay, that is not in the interval. So we know, just looking at that interval, that we are going to reject our hypothesis, because we can see here, since it follows these two rules, as long as 68 wasn't going to be in our interval, then we knew that we had evidence that it was going to be something other than 68. And more specifically, it looks like from our interval here that it's shorter than 68 inches in our building. Now, keep in mind, if these two rules here do not get followed, okay, if we use a 99% confidence interval and a 5% significance level, then the puzzle pieces don't go together perfectly. Or if we use a greater than or less than alternative, the puzzle pieces will work most of the time, but there will be times where it doesn't, and so we can't just interchange them fairly. The last part of this front page we will talk about in a separate video. So I'll put type 1, type 2 error, and power in a separate video. Moving on to the second part of this study guide, which is the two sample. If I were to take a similar topic as on the first side of this and say, I want to test if the mean height for males in the high school is roughly the same as the mean height for females, or are males statistically significantly taller? Okay, so if I wanted to test this, first of all, I would give my hypotheses. You can use whatever subscripts you want. M and F would make probably the most sense here for male and female, but you're going to explain what each one is. Okay, so in this case, I could use one or two, or I could switch these to M and F, and I would say then mu sub M is the mean height for Minnetonka High School males and students, and that mu F is the mean height for Minnetonka female students, high school female students. And so you are explaining what each one is, what each one stands for there, and that would be the first point. And the second point here would be typing conditions again. So in this case, it's now a two sample t-test. And again, as long as you write that, that takes you out of the work of writing some of this formula later on. And so it's a big thing to write two sample t-test. The conditions, what we have here is that it's two random samples. And again, we'd be depending on the question to state that again. Okay, that there's a random sample of males and a random sample of females that are included. Keep in mind, if this were an experiment where we had, say, 50 volunteers and we randomly assign them to two groups, then instead of random sample, it would be a random allocation or random assignment. So be a little leery or weary of that it's that if it's a sample, you know it's two SRSs, but if it's an experiment and it's not like a survey or something, if it's an experiment where you're truly just randomly putting them into two treatments, like a placebo and an experimental drug or something like that, that would be a random allocation instead. In this case, it was just random samples of males and females because we're just going to survey based on height. The fair to believe that the sampling distribution would be normal. Keep in mind it's both now. So for both, it would have to either tell us, give us n is 30 or more, or that we'd have to create the box plots. In this case, I'll just say that it was 50 for each gender. So n sub m and n sub f would both be 50, which of course is greater than 30. And so the central limit theorem again would tell us that it's normal. And central limit theorem again goes back to the sampling distribution unit. Tell us that the sampling distribution is normal. Okay, now the last piece here, the additional condition that we have for a two sample is to note that the two populations are independent of each other. The two samples in this case were collected from independent groups, that the males and the females aren't affecting each other for height, which would be very clear, I think, to follow here, unless we found a bunch of siblings who are really tall together and are one of each gender or anything like that, where we didn't do that fairly. But that they're independent of each other is just something that you need to state. The only way a question would ever note is if it says an independent random sample of females was also selected. Then it would be telling us the independence right out of the gate. Otherwise, you would just be using a statement that, just to recognize that that that's important. And so you just be writing something like, it is fair to believe that the two populations would be independent of each other. And that's all you would need to say there. Nothing else from the question to support that. Finally, there is that whole 10n is less than capital N that you may see periodically, but I would not put too much worry about adding that on a 2-sample t-test. Typically is not shown up on rubrics. Step 3. Step 3 here is in the calculation of the t, the degrees of freedom, and the p-value. Now this gets a little more involved on a 2-sample, but again, as long as you have denoted that it's a 2-sample t-test, then you can avoid writing this formula. And what you would do then here is, because I put males first in the hypotheses, males would be the first group here. So for instance, males might have an average height of 69 inches, let's say. So I'm going to make this 69. And let's say their standard deviation is 3 inches, and I selected 50 of them. So this would be 3 squared over 50. Sorry, that's 3 squared. Tough to see there. And then let's say females' average height was 67 inches, and their standard deviation was 2.5. So that'd be 2.5 squared over 50. Okay. And now I would probably just go to my calculator and I would just calculate this. Now, again, keep in mind my HA here. I have to point out that in the calculator, my HA is a greater than. So I'm going to go to a greater than on my calculator. It's going to ask you if you should pool it. You never have to worry about pooling it. So just leave that as a no and then calculate. And what I get here then is I get a test statistic of about 3.62. I get a p-value of about 2.36 times 10 to the negative 4. So we've got 0.0002. And then I also get a degrees of freedom. And the degrees of freedom it gives me is about 94.9. Now, on a 2-sample, I really would advise taking degrees of freedom from your calculator. Your calculator uses a formula that's pretty ugly, but makes this way more accurate. And so it's going to get something that's better off. And the most degrees of freedom you could get with this problem would be 98, which is basically 50 minus 1 plus 50 minus 1. The conservative approach, if you didn't use your calculator, is you have to play it safe, which would be 49 degrees of freedom. As you can see, one less than the smaller sample size. But your calculator did a little calculation based off how close the standard deviations are and used the sample sizes to get to 94.9 degrees of freedom. Now, the p-value, again, is the likelihood of us achieving the result that we got, assuming that males and females are statistically are the same height as populations. Okay, so assuming the null is true, we're saying it was about a tenth, hundredths, thousandths, 10,000, 2 in 10,000 difference that we found if males and females truly were the same height. In other words, we would have gotten an extremely rare sample here if males and females were the same height. And so we probably have evidence here, provided we got a random sample and everything, we've got evidence that males are statistically significantly taller than females. Again, the reason being here is we got such a rare sample that it's just not realistic to believe that we got that 2 in 10,000 sample. It's more realistic to believe that we're actually HA won out in this problem. So for our conclusion, we'd say based on our evidence, our p-value being 0.0002, which is less than 0.05 or 0.01, whatever we'd use, we are going to reject our null hypothesis. So there is evidence to support the alternative hypothesis that Minnetonka High School males are statistically significantly taller than Minnetonka High School females. Okay, again, we always end with the idea of speaking to HA in context because that's the question that was asked. Do we have evidence that Minnetonka males are taller than Minnetonka females? And that's how an AP exam question would be asked as well. Is there evidence that this group is bigger, smaller, different than this group? Or if it's a one sample, is there evidence that it's greater than this number or less than this number or whatever it may be? So that would be our 2-sample t-test. And then finally, our 2-sample t-interval. Our 2-sample t-interval begins with that sort of optional step again of the thesis statement. The one thing I really like again about the thesis statement is I can tell the reader what's going to go first. So I would be estimating the difference in mean height, Minnetonka males minus Minnetonka females. So I would be noting somehow that it's mu sub m minus mu sub f. So that's telling the reader it's always going to be males minus females, and it's difference in means. Okay, there's a matched pairs scenario that I'm not talking about in here right now, but that's a mean difference. This would be difference in means because there's two of them. Okay, so with that, then with us estimating this difference in means, what we are doing is we're just taking our samples, which again had an X bar of 69 and 67 respectively, an S of 3 and 2.5 respectively, and sample sizes of 50 each, and we're going to estimate what that difference in height is between males and females. Keep in mind, we're probably going to get something that doesn't contain 0 because we've already shown that statistically significantly males are taller. This is a 2-sample t-interval. Same conditions as above. We need random samples from both. We need to verify normality, which would be one of those 3 options between telling us 30 or more or having to graph it. We need evidence that or at least state that the populations are independent of each other. And then there's that 10n is less than capital N, just saying that we took a small portion of the population to be in our sample. So that would cover the type and conditions. Now that's going to be your first point here. The second point, as we noted above, you're going to take degrees of freedom most likely from your calculator. Okay, so in our situation, the X bar 1, the S sub 1, and the N sub 1 are the male information again. The X bar 2, the S sub 2, and the N sub 2 is the female information. And we would now take this as a stat test. This is a 2-sample t-interval, which is down a ways on your calculator. Make sure it's t and not z. Okay, 2-sample t-interval. Okay, and we then put the values for male and female in. Keep in mind, we're going to put males numbers in first because we said up here that males are going to go first. And so I put the 69, the 3, and the 50 in for the males. Then the 67, the 2.5, and the 50 in for females. I'm going to make it a 95% confidence interval. I will not pool it again, and then I will calculate. And when I calculate this, I'm going to get an interval here of 0.9036 to 3.0964. Okay, and this is now with, and you have to state this, 94.9 degrees of freedom. If you do not include degrees of freedom with your interval, then you're going to get only a partially correct in that problem. Okay, the degrees of freedom are going to, if we use the different degrees of freedom, we are going to get a different interval. So if you use the 49 here, that conservative approach that I talked about, you would get different values here. And so you need to make sure you align these two, the interval with the degrees of freedom in this case. Okay. Finally, our interpretation here, we are 95% confident that our interval, and again, I just use 95, that our interval from here to here, which is the 0.9036 to 3.0964, that interval contains the difference in heights, males minus females, at Minnetonka High School amongst the students. In other words, we are 95% confident that males are somewhere between 0.9 inches and 3.1 inches taller on average at Minnetonka High School. Okay, and that's with 95% confidence. So that just means if we ran this interval 100 times, 95 out of 100 on average would contain that actual difference. What is that difference? We have no idea. Could be 1 inch, it could be 3 inches, could be 2.2. We don't have a clue. In fact, this one could have even missed it because again, 5 out of 100 will miss that difference. But this is pretty convincing here that 0 is not in the interval and not even really that close to being in the interval. So it's pretty convincing here that since 0 is not in our 95% confidence interval, that we have evidence that males are statistically significantly taller. Notice how when I said that, I noted again that this is a 95%. So a lot of times you'll get the follow-up question from your interval, is there evidence that males are taller, presuming we hadn't run the test already? And you would say, since 0 is not in our 95% confidence interval, that we have the evidence that statistical significant evidence that males are taller. The one thing I didn't talk about here that I just referenced was match pairs. That will be in a separate video devoted just to the match pairs, which is a very common one sample t-test that's used on the AP exam. As always, if this leads to any questions, please ask. Thanks for listening.